Hello and welcome to another episode of How to Make an Operating System in Rust on aarch64. Today what I'm gonna do is I'm gonna add input functionality to serial.rs. So yeah, let's start with that actually, and then we will see what else we are gonna do. So what we're gonna do is we're gonna add serial getchar. And we are going to just get a self, since we are not writing, we're just reading. And we're going to return an option of U8. And honestly, it should probably be a character, since we are getting... Yeah, let's make it a character. Then what we're gonna do is we are going to say that unsafe, and if self.uart_other, we add hex 18, which is the flag register of the UART. Read volatile. And we are going to end this with 1 shifted by 4, so we're getting the 4th bit only. And we're going to say if that one is equal to 0, then we have something in the buffer, so we return some self uart other read volatile. Okay, otherwise, if there's nothing, if this if statement does not evaluate to true, we are going to return on. Then in main, we're going to say let's just use the loop for now, and we're only going to do this on 1 core for now. So let's see, we're gonna yank this line at this. Oops, let's do 2. Oh god, what am I doing? Anyway, if the CPU ID is 0, let's loop. And we want, what do we want? We want to put this in a scope. Then let console equals 0 console dot acquire. Then on console we are going to get serial getchar. We're gonna return the option here. So let c equals this, and then if let some character equals c, then we're going to just print this, and we are going to print the ch. Let's see what it says, or where we made a mistake. Okay, I saw one thing. We have to put a semicolon here. We misspelled acquire. Tuple. Influences SU8. Okay, yep. So in serial, we want this U8 as char. Okay, then let's run this. We're seeing hellos, and we can type. So what we're getting now is we can input something. So what we can say, let's say let's see. Can we do something with this? I guess so. We can say if the character is C, we print hello world. And we're saying if ch equal, let's say C. Or let's say H actually. Then we will print hello world. Okay. Let's just try this out of fun and games. Press H and it says hello world. Anything else does not print anymore. So that means we now have a way to get input into the operating system. Next thing that I want to do is, let's see, what else can we do? I would actually want to put some stuff into memory.rs so that I can have like a memory map in there. Since we are only targeting QEMU, let's go and only get it here. We are going to create memory.rs. We're gonna save this. And we are going to, or actually, do we call it memory.rs? Call it memory map.rs. What we're now gonna do is in main, we specified the serial address. I'm gonna grab that. I'm gonna put this into memory map. And let's see, did we define anything else? I don't think we defined anything else for now. So here we're gonna mod memory map. And we're gonna say use create memory map everything. And in theory, this should not compile. Okay, let's see. Not accessible. Of course, we have to make a pub. And there we go. Now we have a file where we can put all the devices and such. We can define them. Let's see. Do we have anything else? No. I think that's all the devices that we're using right now. What I would do now is in platform.rs, I would define some functions so that we can actually more or less accurately wait for a certain amount of time. So let's see. We are going to yeah, let's make a function get system timer and return a u64. And here we're just gonna read MSR, and we want counter, what was it called again? 1 second. Counter CT. Yes. CT EL1, or rather EL0. That gives us a timer. Get system timer frequency. It's gonna return a U64.2 and MSR. Okay. Let's see. So now we get the frequency, we get the timer. What I now would do is we want to write delay functions. So let's start with pop delay ticks. We're gonna take an amount of ticks as U64. And first, we're gonna get the start time. Then, while that system timer minus start time is less than or ticks. While that is the case, we will just stall. Then what we can do now is we can go up the chain basically. We can say function delay microseconds, and we're gonna say this many microseconds, or let's call it just microseconds. It's gonna be a U32 because ticks only takes the U64. If we delay by a factor of, let's see, what's microseconds? We have in hertz, so this many ticks in, it's like megahertz. Anyway, we know with the timer frequency how many ticks are in 1 second. So what we're gonna do is we are going to define a const microseconds factor. It's gonna be an F64. Let's just use floating points, and that's gonna be 1, 2, 3, 1, 2, 3. If I am right, and then we're gonna say delay ticks. Gonna take the microseconds as U64. Gonna multiply that by the frequency. And then we're going to cast this as a float and do this. This has a few like rounding errors for sure, but it's accurate enough, I would say. So what we're doing is we're getting the system timer frequency, which is how many ticks we have per second. Then to get a big number, we multiply this by the microseconds, because we want microseconds later on. And then this is basically a division. We're dividing by some number, but instead we're doing with a multiplication. And before division, we always want to multiply, since we get less, we're losing less precision this way. So let's do the same thing for delay microseconds. This also takes a U32, and it's basically the same thing. But this time we're gonna take only this small of a factor, and other than that it's basically the same formula. So we're gonna say delay ticks. It's gonna take the microseconds as U64 times get system timer break. Then this as F64, we're gonna multiply it by the factor. And we're gonna get this as U64 for the function call. Yes. And the same thing for seconds. Seconds is gonna be pretty easy. Seconds is just gonna take the timer frequency. So we don't need a constant, we just delay 6 seconds as U64 times get system timer frequency. And that is it. Because the system timer frequency, as I said, is how many ticks there are in a second. So if we pass that to delay ticks, we get 1 second. And if we want more seconds, we just multiply it. And that is it. So what we can do now is in source main, let's try this real quick. Instead of doing this 0 console thing, oops. We're going in a loop. We're going to do kprint line. And I'm just going to do get system timer. I'm going to print a timer. And then I will delay for seconds, and let's say 1 second. Built. Okay, we have errors. Yes, we want to use create platform. Let's import everything. We are putting platform in here. Okay, delay ticks. We of course have not seconds, but we put S here. Then ASM. And of course, they need to be unsafe, all of these instances. Okay. This one does not need to be unsafe. These do not need to be unsafe. Okay. I have a typo here. That one is called PCT. CNT. PCT for physical counter. Okay. Let's run it. And now we should get roughly every second a print. Okay, so let's also do one thing. I'm gonna print the timer frequency before we start looping. Timer frequency. System timer frequency. And now let's see, the timer frequency is 62.5 megahertz. And if we look at it, well, it looks about right, yeah. So now we have delay functions. Now we can pair those with maybe some sleep functions or whatever. Like put a processor core in a low power state and then wake it up when the time is up. Stuff like that maybe. But yeah, it's also useful for things that you don't want to have that you don't want to happen all the time. Like it's still a busy loop, so if we look at the utilization real quick, here we're gonna go htop. Oh, it's not installed. Let's install it real quick. Now, if we look at the utilization, it's still 100% because we are still, yeah, we're still pulling the value the whole time. To fix that, what we can do in platform.rs, we can make one more function. Let's maybe put it down here, and let's call it pop function. What would we call it? We will call it hold processor wait. Let's just call it for the what the instruction is. It's called wait for interrupt. And here we're gonna say unsafe ASM, and we are going to first do a DSB SY, which means a system-wide data synchronization barrier. That just makes sure that all transactions on the core are finished before we do the WFI, which is the wait for interrupt. And now, since we're not doing anything on cores, the other cores, so this is only executed on core 1, let's actually put them into the wait for interrupt state. Build and run. And now we check htop again, and we see that there's only one core that is at 100%. The other ones, here. The other ones, they're basically sleeping. And that is how you do like a little bit of power management. Okay. There's another instruction that is called wait for event, but QEMU does not implement this one as far as I know, so we're still gonna write the function. It's basically the same. Except WFI, we do WFE, and then we could, if it would like work, we could say send event, and we could do something like SEV, which means send event, and then the other core would wake up, but I don't think QEMU implements this, so let's see. Let's do a wait for event, and then build and run, and let's have a look at the... No, it doesn't seem to implement it. They're still running. They're still looping. So it's basically a no-op on QEMU, as it seems. Yeah. I think that's all that I wanted to show today. So what we did, we put the one device that we have into the memory map, which we are gonna fill a bit more in the next few episodes, like for RAM start, RAM end, and so on, so that I don't have to deal with the device tree just yet. And we made our serial able to listen, so we can send keystrokes to our serial now. And in platform, we implemented delay functions and power saving functions, or wait for interrupt and such. Yeah, I think that's it for this episode. I hope you enjoyed, and see you in the next one.